Key concepts in metabolism and thermogenesis for energy balance. Basal metabolic rate, BMR. The basal metabolic rate, BMR, is the amount of energy expended while at rest in a neutrally temperate environment and in a post-absorptive state. BMR accounts for approximately 60 to 75% of total energy expenditure in the average person. It is primarily determined by lean body mass, with muscle tissue being a significant contributor to the overall metabolic rate. Resting metabolic rate, RMR, versus BMR. Resting metabolic rate, RMR, is similar to BMR but is measured under less restrictive conditions. RMR is usually 10% higher than BMR and can be influenced by factors such as recent physical activity and food intake. Both RMR and BMR are crucial in understanding the energy requirements necessary for basic physiological functions. Thermic effect of food, TEF. The thermic effect of food, TEF, refers to the increase in metabolic rate after ingestion of food. It accounts for about 10% of total daily energy expenditure. Proteins have the highest thermic effect, increasing energy expenditure by 15 to 30%, compared to carbohydrates at 5 to 10% and fats at 0 to 3%. Physical activity and energy expenditure. Physical activity is the most variable component of energy expenditure, potentially accounting for 15 to 30% of total daily energy expenditure. Non-exercise activity thermogenesis, NEAT, which includes all physical activities outside of structured exercise, can significantly impact overall energy balance. Adaptive thermogenesis. Adaptive thermogenesis refers to the body's ability to regulate energy expenditure in response to environmental changes such as diet, temperature, or exercise. This process involves brown adipose tissue, BAT, which generates heat through uncoupling protein 1, UCP1. Adaptive thermogenesis is a key factor in weight regulation and can vary significantly between individuals. Shivering thermogenesis. Shivering thermogenesis is an involuntary response to cold exposure, where muscle activity increases heat production. Shivering can increase the metabolic rate by 2 to 5 times the basal level. This is a short-term mechanism for maintaining core body temperature in cold environments. Non-shivering thermogenesis, NST. Non-shivering thermogenesis occurs primarily in brown adipose tissue and is stimulated by the sympathetic nervous system through norepinephrine. It is essential for maintaining body temperature in neonates and in adults exposed to chronic cold. NST is more energy efficient than shivering thermogenesis. Role of thyroid hormones. Thyroid hormones, particularly triiodothyronine, T3, and thyroxine, T4, play a crucial role in regulating metabolic rate and thermogenesis. They increase oxygen consumption and heat production by stimulating mitochondrial activity and uncoupling proteins. Hypothyroidism leads to reduced metabolic rate and thermogenesis, contributing to weight gain and cold intolerance. Leptin and energy homeostasis. Leptin is a hormone produced by adipose tissue that regulates energy balance by inhibiting hunger and increasing energy expenditure. Leptin signaling affects the hypothalamus, influencing sympathetic nervous system activity and promoting thermogenesis. Leptin resistance, common in obesity, leads to impaired energy regulation and decreased thermogenesis. Clinical condition, hypothyroidism. Hypothyroidism is a condition characterized by insufficient production of thyroid hormones, leading to a decreased metabolic rate and impaired thermogenesis. Causes include autoimmune destruction of the thyroid gland, Hashimoto's thyroiditis, iodine deficiency, and thyroid surgery. The pathophysiology involves reduced stimulation of mitochondria, decreased expression of uncoupling proteins, and impaired sympathetic nervous system activity, resulting in symptoms like fatigue, weight gain, and cold intolerance.